My name is Amelia Brey. I introduced myself a little bit before. I'm a composer by training with a DMA in composition. But while working on my doctoral research, I joined onto an interesting corpus studies for machine learning project, which I'll get into a little bit. It's nice that we have some data science, machine learning people with those interests here today, because I have something interesting to present. People usually bring a personal project. This is a project I was on the team for, really as a quality assurance and subject matter expert. I'm going to open the PowerPoint now. Thank you for the title again. What 1,000 pieces of music, if not 10,000, or more like 1,000 in this corpus, 1,000 pieces of music can teach us. A data-driven look at the DCMLab Corpora. There's a lot of words in there. So let's break this down a little bit. DCMLab is a digital and cognitive musicology lab at the École Polytechnique Fédérale de Lausanne. French is okay, I think, in Switzerland. Several of us have joined on as remote contractors to complete this. The corpora are built of music harmony annotations where we've added chords into sheet music and can study these with various data science and machine learning technologies. Data-driven look is using hard data extracted into data tables, but we'll get into that. Our publication is called the Distant Listening Corpus. This is a publication of 1,283, actually, music scores, composers including Bach, Beethoven, Mozart, Chopin, and Bartók. This is one of the larger published resources of annotated sheet music. These are typeset in MuseScore 3, not MuseScore 4, MuseScore 3, using either public domain or Music XML sources or through newly commissioned annotations. My PA, Johannes Henschel, has written a MuseScore 3 parser library for Python. This can extract not just the notes and measures from these MuseScore files into data tables showing exactly where each note in the piece is, but also can parse newly added harmony Roman numerals. I'll get into a little more detail about those into a machine-readable format such that they can be analyzed statistically. There's a team of us that are music theory experts by background, with some background in computing, but primarily music theorists, whose job it has been to cut through the many, many layers of subjectivity that comes to interpreting the harmony of a piece, and then make sure we have really good solid encodings that a computer can work with. For those of you who have not taken music theory, I'm going to give you a little primer on the importance of functional harmony, why we use it. Groups of notes simultaneously make chords. You've probably heard of chords. And these are recognizable auditory signatures that demarcate sections of a piece of music. I'm going to show my age and play a very millennial little comedy ditty here about all of the songs that can have the same chords. Thank you for the suggestion.
Recognize this?
Yeah, that's Don't Stop Believing by Journey and the cast of Glee.
Yeah, there's a few more songs with the same chords. Check it out.
My life is brilliant, my love is pure. I saw an angel, of that I'm sure. People kill and people dying, children hurt and you hear them crying. Can you practice what you preach? Won't you turn the other cheek? Forever young, I wanna be forever young. I won't hesitate no more, no more. It cannot wait. I'm your lipstick stains on the front lobe of my left side brains. I knew I wouldn't forget you if I could. Then I would. I'd go wherever you will go.
That's enough of that. So you can sing all of these over the same basic accompaniment. And if you hear classical pieces like those of Mozart or Bach, you will hear, particularly Mozart, you'll hear a succession of chords with a melody extemporizing and developing over it. But you could reduce it down to those chords and try to look at the form of the piece that way. No, no, no. There. To give an example of what this looks like in sheet music, I've written a reduction with many, many parallel fifths of that four chord song group. 1, 5, 6, 4. And underneath the staff, we indicate that the key is C major. And then 1, 5, 6, and 4 refer to how many scale steps that is above the note C of C major. These are written in Roman numerals. If the chord is inverted, turned up on itself, you'll add numbers after it. The details of this are known to those of you who study music theory and are a deep dive for those that are interested in exploring it more. This is a piece some of you may have heard, and I'm going to show how we handled this, both in musical analysis using harmony annotations and in data analysis. Hard to interrupt that piece, but I'm afraid I'm going to have to get through all of this material. This is what this looks like in sheet music. This is a screenshot from the annotated MuseScore file that we took in. It's a single moving line. So you can't immediately indicate, okay, we have the notes G, D, and B, G major chord, at the same time. We can't immediately indicate that. We can, to a trained ear who's used to hearing these things repeated throughout the measure, suggest that G major is the chord that's operating throughout this bar. It's not all members of the G major chord. There's an A. There's no A in a G major chord. But one can hear, if one's used to listening to music, or if one is a good performer, that the A is a decoration. How we annotate this, we say the key is G major, just given in the signature. The first note is G, so you can guess that the key is G major. The chord 1 is the first degree of the scale G major. The G major chord, G, D, B, or G, B, D, we stacked it in thirds. There's one other little detail, which is a subtlety. For those of you who have studied music theory, there's a pedal point. The note G is a pedal 1. That means the note G is held underneath as the chords change. And we show that using a square bracket. For those of you who've studied music theory and are interested in this, I can absolutely address more detailed questions about this. We put quite a lot of effort into developing a really consistent standard that had minimal subjectivity and could largely be parsed by a computer, but also embraced the different ways of hearing the music theorists could bring. Now, let's get into something cool and technological. The parser highlights which notes are the non-chord tones. So that A is not a member of the G major chord. The computer knows that the chord 1 in G major is G, B, and D. It looks for those. It says, okay, these notes are in the chord. And then it sees another note that's not, it marks it red. And then we get a reviewed file that shows all of these. If you feed it into parse, it can also check the analyst's work, because If the non-chord tones, the red tones are above a certain threshold, it'll tell you, hey, did you mark this correctly? Because you've marked more than 2/3 of the notes as non-chord tones, just make sure to proofread this. So this is something that we do in the process of preparing these data sets. So having the red notes here is really, really useful for seeing how harmony operates. There's another app that some other people in the lab are developing where you can do reductive or Schenkerian type music analysis by reducing a score to fewer and fewer notes in an applet. We haven't found a way to synthesize these yet, but there's definitely some potential there. Yes, it can't detect automatically what the chord is, because how would the computer know that it's 1 in G major or 5 in C major? Because there are many different key contexts that the same notes could be in. So this is why we need a human annotator here. This is what the MS3 extract command, which is the Python command that gets data tables from this music, looks like. It's a very, very big graph. I only selected a few columns of it. I didn't actually even select the columns far to the left of this that show what measure we're in, what beat of the measure that we're on, and what the actual harmony was. But the parser here, these are successive labels from the previous piece of music that we saw, shows what the chord tones are. And this is actually in a stack of fifths. So there's 1 and then 5 perfect fifths up and 2 perfect fifths up is how we've encoded the chord tones. Root, bass note. Here's something interesting that they've done some genuine machine learning research on. Number colored, number untouched. So under this label, the G major label, there were 2 colored tones, the A's, and the number untouched, 14 chord tones, members of the G major chord. Count ratio is the proportion of notes that were colored in the measure. And this has been used by people who know a little more about this math than I do to create a probability field that could indicate, how many notes are likely not to be chord members in a chord of this type. We're going to get to some data that visualizes that later. And then to the right, we have duration ratios. So number of note heads, which in this case is going to be the same because they're all 16th notes. But if the notes were different lengths, we would get different values for duration and number of notes. Here is some cursory data analysis that I did using a pivot table. I tried to show the count ratio of non-chord tones, not members of the labeled harmony, per chord type. So the 1 chord is the G major chord in G major, 2 is the A minor chord in G major, 5 is the D major chord in D major, and so forth. I averaged the ratio of non-harmonic tones and grouped by which Roman numeral that was over, and found that, for example, the seven chord in a major key, which is diminished, was likely to have about 1/3 of its members non-chord tones. So there's much more decoration with passing notes and so forth on a 7 chord than there is on, for example, a 4 chord. The C major chord in G major had the exact value was 0.16 repeating non-chord tones per chord tone. And last but not least, we've used pandas data frames to generalize the entire catalog. So this is, again, for Bach, the total distribution in the number of duration and quarter notes of a certain type of chord over a chord root. So the P1, we didn't use the Roman number, we used the root of the chord's interval to the tonic, which is basically the same thing. Perfect 1 would be G and G major. Perfect 5th would be D, G major. And then for chord types, we can see that the blue major had this many duration, a little under 2000. And the orange for minor had this many, more like 1500. So there's a few more major tonics than minor tonics in here. For those who, yes? Here it's more of a matter of just showing the total number of things that were in the corpus. If we were to show like the change as the composer's opus progressed, like if you had later works that were looking different, you might use more of a line graph for that. And we have many, many, many of these analyses, as you pointed out. For all of the composers in the corpus, we've got a stock data report code that gets you figures like this based on any number of input scores. These are on GitHub. You can get them. Let's actually look at that. Let's click some links. For those of you watching at home, is my screen sharing still working? Am I on a github.io page? This is the front page of the corpus and the DCML Corpora. This is a GitHub repository. I can give any of you the link if you like, or are you going to upload the slides to later? So you can click the links in there. Anybody have requests for a composer to look at? Yeah, let's look at Chopin. So we have folders here. Instructions on using the metadata, which has many, many columns that are usable for different types of analysis. Folder of chords, folder of harmonies, measures, and note files. There should be, here's the github.io link for it. There are similar data analyses too. I'm trying to find exactly where they showed up in the github.io page. Analyses. So for Chopin, you can get, let's look at cadences. This is an interesting one. Should probably have turned my VPN off. It's a little slow. There we are. So this is what the front of the harmonies file looks like. We have measure count, measure number, total number of quarter beats at that point, duration in quarter beats. And the cadence labels, perfect authentic cadences, inauthentic cadences, half cadences. So for the whole distant listening corpus, we have 59% cadence types. Where's the legend? I believe that's perfect authentic cadences. And then a pie chart showing breakdown of others. There is a lot of opportunity to dig into these kind of graphs and make, different elaborations on them that show different details, can be highlighted to show different things. And here's the total number of perfect authentic cadences, count 0.59, half cadences, count 0.19 within the corpus of Chopin mazurkas. How many times he used a perfect authentic cadence is a 5 chord going to a 1 chord with the tonic of the scale degree in the upper voice in the final chord. And then a half cadence is when a phrase ends on a 5 chord and then can be resolved afterwards. So this is an example of how to navigate the data, and we have a lot of preloaded analyses you can use if you're interested in exploring. This is the report published in Scientific Data explaining the exact design, presentation, history, and details of the project. So if you want to, on your own time, click through this. There's quite a lot to read. And some machine learning applications. These were some other members of the lab took the data and applied a Bayesian model to attempt to determine which chords are likely to be chord tones and not chord tones, depending on the type of a chord. And they'll talk through the math in some more detail, how they did this. Select a note type, can draw a pitch class from a chord tone distribution or figuration tone distribution in return to get a model. And here it's showing probability of chord tones versus ornaments. Again, depending on the chord type, in a major key, in a major chord, a minor chord, dominant seventh chord, intervals above the chord. So a perfect unison is most likely to be a chord tone, of course. A perfect fourth and a dominant seventh chord is likely to be a non-chord tone. So we don't have any examples of chord tone indications for that. The one on the right is a set of scores that we did not originally commission. So this doesn't actually, this model's based on the annotations that we did, but doesn't necessarily rely on them. So here are some MuseScore files that we didn't annotate, some of which have shown, for example, a perfect unison as an ornament. The question is, are the styles represented in here more likely to actually have harmony used that way, or are they quirks in the proofreading? That's not answered here. That's a topic for further research. And that's it from me. If any of you have any questions, I'd love to discuss this. We're only just now exploring some of the applications of this. We're pivoting the project right now towards looking at actual formal spans, introductions, conclusions, and so forth of a piece, elaborations of a motive. But there's a lot of possibility to be done with the harmony as well that I think we've really only scratched the surface of so far. This has been an exciting project to be involved with. I'm glad I got to share it with all of you. And if you have any thoughts for discussion, or if you've brainstormed any ideas as to what we could do with this data, I would love to hear your thoughts, either here or on our own.
Yeah, so I guess kind of a question, kind of a comment. I noticed looking at the composers that are listed, I don't know if there's any more, but like they all seem to be pretty composers that stick generally to like notions, like the traditional kind of Western idea of music, right? Like I didn't see like a serialist on there. And I was thinking, you know, maybe if you did have a serialist, all the notes would be read, right? Maybe not, but I was just thinking, like, was that something that was done on purpose to stick with people that are sticking to a more traditional conception of harmony, or is that just how it played out because it was easier to get the training data started, I guess?
So our earlier publications really were a little more bound to the Romantic period. A lot of this is because this is the root of the practice as we analyze it now. Before the Romantic period, harmonic notation was much simpler. Since then, it's gotten a lot more complicated. It's great that you say that, because having established these precedents, we are a little bit limited by what's public domain. So we can't get too far into the 20th century without copyright issues. However, we've been able to get up to Bartók, Erwin Schulhoff, who is a very jazz-influenced composer, some outright jazz scores as well, with these precedents having been set. And you're right, there are a lot of red notes, but it's not all red notes. You can identify a triadic structure in a lot of this music. And this gives us the opportunity to really quantitatively identify how much did the harmonic precedents break down in the 20th century? Because on the one hand, to people who've studied harmony to an extent, that type of music sounds like it's all coming out of nowhere. On the other hand, it absolutely has a triadic tonal structure somewhere deep in the back. Or if it's from a non-Western tradition, it may have either had some contact with a Western tradition, or have had some contact with a different tradition based in the harmonic series, ergo having resultant triads out of dealing with that. That is really on the cutting edge of what we're trying to work on. So I'm glad that you brought that up.
Yeah, so going back to the older music, without, what you just, the issues you just introduced, you said it required an expert listener to actually annotate the harmony to start. So presumably now that you have all this training data, that can be automated?
Yes and no. Yes, because we have precedents established enough to engage the computer in dialogue with the accuracy of our work. No, because we haven't actually found an objective signifier for what key you're in, other than that it sounds like you keep coming back to that, which is an entirely intuitive thing. We might in the future, through some kind of machine learning research, find that there's a consistent indicator, but we haven't found one.
I mean, that's.
There are conflicting schools of thought about it, though, which is the hard thing. And sometimes we disagree amongst ourselves, the annotators, coming from different traditions of music theory. Some of us will have studied Schenker, some of us will have studied Riemann, some of us will have studied something entirely different. And we're working with the same language. We're working with the same definitions of scale steps. So a lot of the time we're talking back and forth trying to determine what an expert listener even hears. Because there's not necessarily consistency there. And we have to default occasionally to precedents of just what the intuition was. Yeah, we're really looking for either the juncture or the disjuncture. We don't really know whether it's there.
Like as you were training to be the expert, like what were you told to listen for, or how do you make, how did you develop that judgment of?
And music theorists have never agreed on this. We don't even necessarily agree on the basic way to do solfege. I learned fixed do. So I basically learned that to intuitively sing all notes as equal according to their fixed pitch without necessarily proclaiming a tonic. And someone who's used to proclaiming a tonic is going to interpret something out of left field as being either extended in the same key, or in a shockingly new key rather than related in two keys. These are conflicting schools of thought. And there's a back and forth also between theory and practice. So composing changed as people started to observe this. There's almost something like with Heisenberg and the particle going on with even how you analyze, because you are affecting how music is made when you analyze it. Because composers are going to learn theory and theorists are going to compose.
Super interesting. And I actually had a question, but I will hold it because for time.
We'll look forward to discussing after.
We should
and
talk after.
do you have my email in the contact info?
I can share it if you want.
Yeah, that'd be good.
Okay, great. Thank you, Amelia.